This is Eastern Tech with the NEDC Challenge. Our goal is to assist those with motor impairments that fall under the Americans with Disabilities Act, while also maintaining infrastructure and proficiently utilizing space in urban areas.
But where are our manners? Allow us to introduce ourselves.
You're just like my favorite song going round and round my head. Like my favorite song going round and round my head. You're just like my favorite song going round and round my head. Like my favorite song going round and round my head.
When deciding our sustainable development goal to focus on for our project, we narrowed our options down to 3 topics: industry, innovation, and infrastructure, reduced inequalities, and sustainable cities and communities. Using Microsoft Excel, we created a decision matrix to help us choose between our top ideas for the topic.
Our best option was to create a staircase capable of converting into a ramp.
This design would be especially helpful to the United States, as many overpopulated cities such as New York City, Los Angeles, and San Francisco lack the necessary space to implement ramps alongside staircases for their various buildings. Even in our home city of Baltimore, there are many instances where both stairs and ramps are incorporated separately, taking up necessary space. For overcrowded areas, ramp creation is often ignored due to the smaller sizes of staircases, creating inequity for all people with disabilities. Using Autodesk Inventor, we created a 3D model of the prototype, using it as blueprints for the creation of our original iteration.
We chose to name our ramp RISE. RISE stands for Ramp Integrated Stairway for Equity, and there's 3 main points to this.
First, the ramp and stairs emphasizes the hybrid of our design.
The word equity is there to remind people of the SDG number 10 and number 11 that we're trying to solve to bridge inequalities.
And the acronym itself, RISE, epitomizes how we are trying to raise those with disabilities to have an equal opportunity.
The Arduino is assembled by using 2 separate stepper motors. Each stepper motor has an intermediary circuit in between that connects both power and the port. This makes sure that the stepper motor has enough power to generate torque and is aligned with the code.
We have railings on either side of the stairs because according to the ADA, an angle of incline off the horizontal plane of greater than 5 degrees requires the use of railings. Our stairs have curved edges because as one stair rotates off of the pivot, it makes a circular shape, which means there might be a little gap if these curved edges were not there. But by having this, we ensure that there is no gap that the user can trip on, and it is a clean, flush movement.
The coding portion of the Arduino utilizes the stepper motor library so that it is able to control each motor with high precision. This starts first by defining in the code exactly which pins in the Arduino circuit board are used by the wires that control the motors, as well as how many steps are in each single revolution of the motor, meaning a higher number would make the motions more fluid, since there are more intervals in between that the motors rotate to. After setting both motors to move at 10 revolutions per minute, we use the code to move the first motor clockwise by a small fraction of 1 full revolution to correctly line it up with the stair above it. We then proceed by doing the same thing with the motor for the second stair, creating the correct angle for the entirety of the ramp. After a delay of 5 seconds, the motors each rotate back down to their original positions so that they are flush with their original orientation and work effectively as stairs once again. Since this is in a loop, the stairs will continue to move and demonstrate their functionality until the code is stopped.
To use the prototype, simply plug the Arduino power cable into a power source. The stairs will then rotate, forming a ramp, allowing all necessary usage by people with disabilities. After a short delay, the ramp will convert back to a staircase.
In accordance to our goal of sustainable cities, we made sure to use recycled materials when designing this prototype. First, we had cardboard to represent wood. This was used for our platforms of the ramp and the stairs. We added wooden dowel rods to represent the firm metal railings and also the axles that were used to rotate the stairs. Since lifting the stairs would require a stronger material, we used thicker chopsticks to lift them. This prototype is at a 1:6 ratio of what the actual design would be. These lightweight and quick materials ensure that we stay true to our goal of efficiency and sustainability. Now, of course, this is a prototype, so if this was made into a real model, the chopstick would be replaced with some sort of pneumatic system that would be stronger and more efficient. Along the way, we had a few issues with some of our designs. Our first iteration lacked sealed edges, and this meant there was a lot of friction when the stairs were trying to go up, and it made it so that there was a different angle each time we plugged it in. To alleviate this, we sanded the edges and used paint to make it smoother to reduce the friction and ensure more consistency.
Some challenges we encountered during this build was the need to generate enough torque to keep the stair in its ramp form. This was a problem as the stair would need to be maintained as a ramp for this build to work. How we solved this was continuous change of angle, the distance from the center of the motor to the end of the support, and the amount of RPMs each motor was handling. Through continuous testing, we eventually figured out and solved our problem and completed the model that we have today.
Our second iteration involved the usage of buttons to switch between modes.
This sketch of the second iteration was drawn so we would know exactly where the buttons would be placed on the model once we made it. In the second iteration, there's an addition of extra wires in the body because of the implementation of the button system. We also swapped out the previous chopsticks with a stronger, flatter material for the lever arm to consistently generate more torque.
In the revisions of this code made to account for the incorporation of buttons on either side, we used two buttons connected to pins 12 and 13 with internal pull-up resistors. That means the buttons read high when not pressed and low when pressed. In each loop, we read the current state of both buttons using the digital read command. We then check if either button was just pressed. That happens when the last state was high and the current state is low. If a press is detected, the motors either move forward or backward depending on the toggle state, which knows where the stairs are currently positioned so that it can move to the correct location. After moving, we flip the toggle to change the direction the next time a button is pressed. Finally, we update the last button state to track future presses in comparison to what was just.
Here, we will demonstrate our stair ramp hybrid in action using a model wheelchair. Starting by pressing the button at the bottom, the stairs will transform into a ramp using the Arduino system. Then we place the wheelchair on the ramp and roll it up. It travels through, staying stable throughout, and then once it gets to the top, the other button at the top of the ramp can be pressed and will transform back into stairs.
One problem that arose while testing was that the wheelchair was too heavy for the ramp to hold up on its own. To solve this problem, we used stronger materials, such as Lego bricks, as the levers to support the segments of the ramp, allowing the wheelchair to be supported.
In conclusion, our prototype of the staircase to ramp mechanism was successful in demonstrating the core functionality. It was able to smoothly transition between ramp and stairs and effectively support the intended objects for testing. This proves that the concept works on a small scale. However, for real-world application, our next step would be to scale it up, ensuring the full-size model is built with stronger materials and more precise measurements. This would allow it to safely support the weight and size of an actual person, making it practical for use in public spaces or other areas where there is a higher need for solutions to accommodate the accessibility requirements of others.
You're just like my favorite song going round, round my head. Like my favorite song going round and round my head. You're just like my favorite song going round and round my head. Like my favorite song going